Okay, so good morning, people. Today we're going to talk about the field axioms, which is a bit of a supplement to what we've been studying about sets and functions. And field theory itself is a very, very deep topic. You can take an entire course on field theory. I myself, I think I took like maybe 3 courses on field theory but between my undergrad and when I was doing my PhD. And still, I don't know all of field theory. So it's really not enough for me to just tell you about field theory in 50 minutes and to give you a couple problems and give you some notes. That's really not enough. That doesn't do justice to field theory. So maybe, next year we'll take it out of the course because that's not really a fair topic. But I'm going to try my best to introduce you to fields. Just quick announcement is that I'm changing my office hours. I'm adding an extra one and I'm moving them around. So that's something that will be on Quirkus. Another thing is that at 7 today, I'm going to have an extra office hour because I want to help people before the quiz comes out. And then one last thing is that in the chat, I'm going to post a link to a feedback survey that I would appreciate it if you filled this out, because it would help me. Just let me know if the class moves too slowly or moves too quickly or how you're finding the lecture so far. Just give me some feedback on how it's going. Okay, and also one last thing, maybe take a screenshot. Here's a little set theory problem I wanted to do in class, but we ran out of time. So try to do this on your own. And this is a bit of a challenging problem because I give you 2 statements and they might be true or false. And if it's false, don't just give a counterexample. Try to fix it so that it becomes true. Try to replace it with some relevant statement that is true. So do a bit more in-depth thinking. Don't just say, oh, here's a counterexample. Say, okay, here's a counterexample. Here's why it's false. But also, here's the actual true thing that it looks like. So try that. Try that problem. Have some deeper thinking. Maybe if I have the time, I'll try to take it up in a video or something. Okay, let's talk about fields. So I hope that you all got a chance to at least read a little bit about fields, but I want to spend a little bit of time motivating to you, what is a field? Why do we even study fields? Okay, so here's an example. Before I tell you what a field is, here's an example of a problem that uses field theory, but you might not know it. So prove that if I have 2 rational numbers, x and y, and if their product is 0, then one of them had to be 0. So if x times y is 0, then either x is 0 or y is 0. And it makes sense, right? You can't take 2 non-zero numbers and multiply them and expect to get 0, right? Like 3 times 2 can't be 0, for example, right? So how would you prove this though? What exact properties do we use? Like, why do we take this property for granted? Well, there is a little algebraic proof you can do for a problem like this. So I want to prove that x is 0 or y is 0. Okay, so let's say like this. Suppose x times y equals 0. I want to prove that either x is 0 or y is 0. If x is 0, there's nothing to prove, right? If x is 0, I'm done. I proved that at least one of these 2 numbers is 0. If x is 0, there's nothing to prove, obviously. If x is non-zero, then 1 over x exists as a rational number, right? When you take a rational number and flip it, like 2 over 3 and flip it, you get 3 over 2, which is still a rational number. So 1 over x, which people also call x inverse, exists. So let's say it exists and it's a rational number. So let's do some math. If I take xy equals 0 and I multiply both sides by x inverse, the equality is going to be preserved. All I did was take an equation and multiply both sides by x inverse. Now I'm going to do this really slowly. Like pretend that you're a robot and you had to interpret each step by step, like a computer does. How would I rearrange this step? Well, if I'm really, really slow about it, I just argue that, oh, I can move the brackets around. Okay. So I have x inverse times 0. And so this property here is called associativity. It's the property that if I have numbers A, B, and C, and I do A times B times C, I can do that in any order. I can do A times B and then C, or I can do A and then B times C. Okay. Okay. Now you might also say, oh, anything times 0 is 0. So x inverse, for example, times 0, that should be 0. So let's do that as well. So I have x inverse. Well, you know what? Yeah, let's do it like that. Let's simplify it one by one. So now I'm using the property that x times 0, or any number a times 0 is always 0. And then you look here and you say, well, what's x inverse times x? By definition of x inverse times x is 1. So this is 1 times y equals 0, just by definition. So I'm using the fact, now I'm running out of space, I'm using the fact that x inverse times x is always 1, no matter what x is. And now I use the fact that 1 times y is y. So this is the way a baby would do this if they were really, really slow. So let's use the property that 1 times y is y. And now I concluded that y is 0. So what I did is I said, if x is 0, there's nothing to prove. If x is non-zero, then y has to be 0. So in either case, this statement is true. One of them is 0. So we conclude, so therefore, or let's say in either case, x equals 0 or y equals 0. And that's the proof. Now, the whole point of field theory is realizing that, okay, I mean, this is the statement I made for rational numbers, of x and y were rational numbers. But if you look at the properties I used, where did I really use the fact that these were rational numbers? I used these properties. I guess I also used the property that 1 over x exists. For example, if x was 5 and I was working with integers, then 1 over 5, in a sense, you know, if you only know about integers, 1 over 5 doesn't exist. And if you only know about integers, right? So 1 over 5 wouldn't have the requisite properties for me to verify this statement the way I just did. So what is it about these properties that makes Q special? I mean, the same exact proof would work if I had worked with real numbers instead. And what if I didn't want to work with real numbers? I could have worked with complex numbers. So anywhere I see Q, I just replace complex numbers. All these properties work in either of these cases, in all three of these cases. So I think what at this point, mathematicians notice the pattern and they say, look, there's a pattern. Maybe if I can figure out the key components here that I used, I can generalize this to other types of objects, not just the rational numbers, not just the real numbers, not just the complex numbers, but there's other fields out there. There's fields with 2 elements, fields with 3 elements, fields with 4 elements, fields with 5 elements. There's other types of infinite fields that I can't tell you about right now. But the whole point of this is noticing that there's a pattern. And so what mathematicians do is they turn this pattern, okay, the second my tablet's broken. One sec. Okay, yeah. They turn this pattern into an observation and a generalization. So what they do is they say, look, if a mathematical object has these properties, and don't try to write these down, it might take you too long. If a mathematical object has these properties, then that proof I did above works, that same proof. In fact, I didn't even use all these properties, but there are other proofs that do use all these properties. And so mathematicians observe and say a field, so like a field F is a set. So this is the definition of a field, is a set with operations plus and multiplication, so dot, let's say, such that these all properties are satisfied. So there's a bunch of properties that look intuitive to you and are satisfied by all the number theoretic objects that we work with every day: real numbers, complex numbers, well, later complex numbers, rational numbers. So the fact that addition is commutative, so x plus y is always the same as y plus x. The fact that x times y is y times x, so multiplication is commutative. Multiplication and addition are associative. There's also these identities here. So identity just means that it's a neutral element. So 0 here is neutral. If I add x to 0, I'll just get x back because adding 0 does nothing. Similarly, multiplying by 1 does nothing. So 1 is the multiplicative identity. There's also this inverses axiom, which I kind of stated haphazardly here, but maybe a clearer way to have said it, well, actually a more precise way to say it, is that for all x in F, there exists some y in F such that x plus y is negative, is 0. And that, then we define negative x to be this value y. It's a definition of negative x. You see a lot of the properties we're taking for granted here, the fact that x minus x is the same as x plus negative x, the fact that x plus 0 is x, all these properties we're taking for granted, we're now axiomatizing them so that we can use them in other contexts. That's the whole point of axioms, okay? So I hope that clears up kind of why we use axioms. Why are we even talking about field axioms? This one also is slightly imprecise. This one's saying that for all x in F and x is non-zero, which I can write like this, F minus 0, there exists a y in F such that x times y equals 1. Okay. Now, this is a list of properties of addition, and here's a list of properties of multiplication. What connects these two properties together is the law of distributivity that shows that addition and multiplication have some relationship. Multiplication distributes over addition. So this last property is kind of a connection. This gives a connection between addition and multiplication. That's the point of distributivity. Now there's one kind of subtle property that I left out here. It's this property. When I take two, for example, real numbers and add them, what I get is still a real number. It's not going to be suddenly some other type of number or some other, like a complex number or something. If I take two real numbers and add them, the result is another real number. So that is a property called closure. If I take two elements of my field, x and y, and I add them, it's still in F. This is one that you definitely take for granted, that a lot of people take for granted. And the same for multiplication. If I multiply two numbers together, I'm going to get another number or an element of my field. And one way to put that, and maybe this will help you remember it, is that x and y, let's say, can't escape from F via addition and multiplication. I can't add two numbers and then they suddenly escape away. They always, when I add two numbers, it stays inside the same field. So if I add two rational numbers, that's still a rational number. If I add two real numbers, that's still a real number. Now, if I take a real number and divide it by a non-zero real number, that's also still a real number. The thing is, well, here, let me give you a poll question, see if you understand all these axioms, and maybe you should take a screenshot quick because I'm going to move this away in a second. Maybe I'll take a screenshot and put it in the chat. Okay. All right, so here's a question for you to see if you understand what a field is. Which of the following sets are fields? And a field, here, I'll open the poll for you. And it's just a generic looking poll. Just select one of the four answers. And you can select more than one. In this case, you're going to have to. Which of the following are fields? Don't jump the gun on this. People are already voting. Think about it first, obviously. Which of the following are fields? And when I say a field has to be a set with two operations, addition and multiplication. So I can't just give you a set. I have to give you a set and some operations on it. If I change the operations, it may no longer be a field. So that's why I told you usual operation. So the usual sense of addition and multiplication. I won't go to an unusual one quite yet. Okay. So that means that you have to take this thing and you have to verify that it has all of those axioms. There's like 10 axioms or something, or I don't know, I didn't count. More than 10 axioms. And you have to do that for each one of these, verify all the axioms. So it's not about just verifying the axioms. It's about kind of recognizing which axioms could possibly fail. Okay, so now I'll have a look at the chat. Okay, somebody's asked, a field cannot include subtraction and division. Actually, it can, right? Because we talked about inverses. X minus X, or sorry, X minus Y would be the same as here. I'll write that down the side. X minus Y is defined to be X plus negative Y. And X divided by Y is defined to be X times Y inverse. So we don't define subtraction and division because, or sorry, we don't include subtraction division in the axioms because they follow from the axioms. So I don't need to include them because they already come directly, they already follow from the axioms. So it does, fields do have subtraction and division. Okay, so it's been about 2 minutes and just over half the class has voted. So I'll wait until 80% of the class has voted, which is coming up real fast. Maybe I'll give you another minute. So for each one of these sets, you have to verify all the axioms, basically. But I'm not giving you enough time to check all of them. So you've got to do something. You've got to do something else. You've got to look at these and try to recognize which of the axioms fails. Okay. Another 20 seconds. Okay, that's it. Let's see the answers. There's more than one answer here. A lot of people saying A, a lot of people saying B, a lot of people saying C. Okay, good. Good. There could be more than one. Let's look back at these axioms. This is a trick question, by the way. None of these are fields. None of them. They're all not, none of them are fields. Let's have a look why. Maybe I shouldn't have spoiled it like that. Let's have a look why. Look at these axioms, right? Addition's commutative, multiplication's commutative, addition's associative, multiplication's associative, x plus 0, x times 1, inverses, division. The hardest, these axioms, right? These are just inherent properties of addition of real numbers. And all of these sets are subsets of the real numbers. All of these are subsets of the real numbers. So they're all going to be associative. They're all going to be commutative. It's the other axioms that fail. It's this one here, this division, these inverses one. Here, let me give you an example. For this first one, this is not a field. None of them are fields. And the reason it's not a field is because what's the inverse? What's the additive inverse of 5? Like 5 is in this set, but the additive inverse negative 5 is not in this set, right? It's not a positive number, so it's not a field. Make sense? How about B? So the numbers between 0 and 1, also not a field. And the reason for that is what? What's an example? Ah, good. Some people are saying 0.6 is in this set, the interval from 0 to 1, but if I do, let's say 0.6 and 0.7, just for fun. But remember, if I add two numbers, I shouldn't be able to escape out of the set. So in this case, if I add two numbers, I get whatever that is, 1.3, which is not in my set. Again, it's not in my, proposed field. So it's not a field because I escaped out of there by adding. Okay. So again, closure fails. Okay. Now here's the next, this one's tricky. Z is closed under multiplication and addition. If I add two integers, I get an integer. If I multiply two integers, I get an integer. Which property fails here? Why is this one not a field? Yep, multiplicative inverse. So 5, for example, 5 is an integer. I'm just realizing now that this is why people, it was taking a long time to vote because people weren't voting, which is the correct thing to do in this case is not vote. So 5 is in Z, but 1 over 5 is not in Z. Okay, how about this last one? R minus Q. This is the set of irrational numbers, by the way, right? It's the set of real numbers that are not fractions. So pi is an example. We didn't prove that pi is irrational. It's pretty difficult to prove that, but I'll just tell you, you can take for granted the fact that pi is irrational. Pi is an element of r minus q. And later in the course, we will be able to prove that the square root of 2 is irrational. Later, we'll prove that. For now, take it for granted. Why is this not a field? Reciprocals again? Yep. Pi is in r minus q. Let's say, sorry, pi and 1 over pi are both in r minus q. So it's not the reciprocals property that's failing. And yet, if I multiply pi times 1 over pi, I get 1, which is not irrational. It is rational. See? And people are saying in the chat, root 2 times root 2. That's another example. Exactly. Root 2 times root 2 should be, if this was a field, root 2 times root 2 would still be in there. But it's not. Root 2 times root 2 is 2, which is irrational. Okay. Awesome. Good. I think people in the chat are getting it. And I think the explanation makes sense. So I want to give you another question that tests if you understand fields. Here's an example of a field you've never seen before, unless you've read the notes. Krista says, if even one axiom fails, the entire thing is not a field. Absolutely. A field has to satisfy all the axioms. So if one fails, then it's not a field. Okay. Here is another question here. I'll give you a poll again. This time it's not a trick question. Which of the following properties of F are impossible? So this is a field you might not have seen before. It was in the notes, but this is definitely an unfamiliar field. A field with 4 elements. And so we know that fields have to have 0 and 1 in them. So 2 more elements, let's just call them A and B. And let's assume that these 4 elements are all different. 0 is different from 1, is different from A, is different from B. They're all different elements. What can you conclude about the elements here? Give you maybe 2 minutes to answer. And if you just give me 1 second, I want to scroll here. Okay, yeah. Just checking what I'm doing next. Okay, which of these 4 properties is impossible? I mean, I should have just put false. Which of these 4 properties is false? It's another, obviously that's possibly a clearer way to put it. Okay, over 60% of people have answered. I'm going to wait until maybe 80%. Yeah, Ortiza, it's okay to discuss, I guess. Yeah, it's okay to discuss. If you know the answer and you just blurt it out, that's one thing. But you said D with a question mark, which sounds more like you don't fully know, which is okay. Yeah, it's okay. It's okay if you don't fully know. But if you do know, then definitely don't just blurt it out. So it's okay. Okay, and then 96 of 818 people have voted, so I guess I'm going to end it here. Share the results with you. D. Overwhelmingly, people said D. So a lot of people did choose the other answers, though. Over 20% of the class for C, for example. Good. D is the correct answer. Good. Good. Does anybody want to explain why D is the correct answer? You can come onto the mic if you want. Would anyone want to explain?
Hello, can you hear me?
Yeah.
All right. So if AB is equal to A,
Yeah.
that means that B must be equal to 1.
Okay. Yeah. How'd you get that?
Because if we have a number A, any number A multiplied by 1 is equal to A.
Number A.
I think
Okay.
that was one of the axioms.
Yeah. Yeah.
So that means if B is equal to A, we already have 1 in this set F.
Yeah.
Which means Like 1 is already there, so we can't have b equals 1 because we can't have a repeating element.
Wow. Okay. Okay. I see. So you're saying that, okay, you're saying that b equals 1 satisfies this property, right? You're saying that a times 1 satisfies this property.
Yes.
So, but 1 is the only thing that satisfies this property, and therefore b has to be 1.
Yes.
Yeah, okay. That's an interesting logic I wasn't thinking of. I think you're right. It is true that that 1 is the only number that has the property that a times 1 equals 1. But the problem, I think, is that you'd have to prove that. You have to prove that 1 is the only number with this property. And let me supply the proof here for you, because I think you're right, basically. If a times b equals a, let's prove this. If a times b equals a, then b has to be 1, which is, and then as Mahad has pointed out, b is not 1. I'm assuming that these all 4 are different. So, okay, so if a times b equals a, let's try the same thing I did earlier. Let's multiply by the inverse of a. And I'm implicitly using associativity here. I should be bracketing this expression, but I know that associativity holds in a field, so I don't need to bracket it. That's the whole point of associativity. The whole point of associativity, let me write that up here, is that if a times b times, if I multiply a and b first, or if I multiply b and c first, it doesn't matter. So that means that the expression a times b times c is unambiguous in a field. Any associative operation, you can string it together in any order, and you're going to get an unambiguous statement. Unambiguous expression. There are operations that aren't associative, and so it is ambiguous, and you have to write this every time, for example, because it's unambiguous. Because this is ambiguous. So I'm not talking about these operations today, because that's something called a Lie bracket, for example, that you can look it up. But anyways, okay, that was just explaining why I didn't bracket it here. But let's move on now. Let's see. The a and a inverse cancel. This is quick math, kind of. And I'm just left with b equals 1. So Mahadis is right. I got b equals 1, which is a contradiction. I'm assuming that b is distinct from 1, because I've got 4 distinct elements. So I'm assuming that, so this is impossible, right? This is false. And I like to write this symbol to mean I've got a contradiction. We'll talk more about contradictions later. So I guess this wasn't a proof. This is more of a justification, because I'm not really proving that b equals 1. I'm proving that b is not equal to 1. Okay, so this is the one that's true. Why are the other ones false, though? Let me take this up in 2 minutes before I give you a problem to work on. Why are the other ones false? Or sorry, no. Okay, I guess the question was which are false. So this one is false, which means it was the right answer to the poll. The other ones are actually true. Sorry, that's double negative. And the reason they're true is you can check what's a times b. Oops, sorry. What's a times b? Well, it can't be 0, because if I have 2 non-zero numbers and I multiply them, that's not 0. That was one of the first proofs I did. So this one's false. It can't be 1, or well, maybe it could be 1. Could it be a? No, it can't be a. We just ruled that out. And for the same reason, basically, it can't be b. I'll leave you to prove that. And so the only possibility is that a times b is 1. So this one is true here. I guess that's what I proved. But inadvertently, I also proved a and b. I also proved these two options as well, because a times b equals 1 is the only true answer here. And a times b equals 1 is the same. Sorry, now I'm getting a bit scattered. Let me move this down a bit. A times b equals 1 is the same as saying that a equals b inverse, which is the same as saying that a inverse equals b. These are all equivalent statements for any field and for any elements a, b, okay? If a equals b inverse, then b equals a inverse. Reciprocating, that's why it's called reciprocating, is because they're the same, is because once you have an inverse of an element, you have the inverse of its inverse, in a sense. So, okay, I hope it's clear why A, B, and C are true while D is false. I feel like I butchered that explanation, but I hope it's clear from what I've written. Okay, so okay, good. I'm on time. We have 20 minutes left. The way I want to spend the last 20 minutes is now, instead of doing multiple choice, let me give you a couple questions on your own to work on. Here's a couple prep questions. Still another one about fields, about identifying whether a set is a field or not. And another question asking you to prove some basic arithmetic laws of fields. Okay, so what I'll do is I will give you 10 minutes to work on this, 9:41. I'll give you till 9:51-ish, maybe a bit more, to work on these three problems. Well, two problems, and the second one has two parts. And I will take it up in the last couple minutes, like the last 10 minutes-ish of class, okay? So 10 minutes, work on this problem. And I'll be on the chat. James will be on the chat if you have any questions. Solid 10 minutes, okay, people? How's it going, guys? Yeah, these properties, I'm just going to add a couple little things about these properties. There's another property. Both of these properties you take for granted. I really like this topic because it shows how the properties we take for granted actually rely on fundamental axioms. So here's one. If you multiply a number by negative x, or sorry, by negative 1, it's just the same as taking the additive inverse. That's one interpretation of this question. Multiplying by negative 1 is the same as taking additive inverse. The second one says that with addition, you can always cancel out something from both sides. And so you have to prove rigorously that you can cancel from both sides. So that's pretty interesting. That's why it kind of fits into the course of Math 102, because it's a proof. It kind of like shows you how do you use axioms to prove something. So it's actually kind of a nice little exercise there. Okay, I'm not seeing any questions in the chat so far, but if you have any, if you're stuck on it, just let me know. And James is there too. Hey everyone, how's the I like the discussion in the chat. I'm the one derailing it and not that's my fault. But how's the problem going? I'll give another 2 minutes to work on it. Does anyone want more time? Can you tell me in the chat if anybody wants more time on this? Okay. Okay. A couple people do. All right, I'll give you a couple more minutes. I think I can take this up pretty quickly. Okay, today we moved at a good pace because I didn't spend too much time reading the chat while I was doing the polls. So that's good. I think I was a better pace today. Okay, I think that's enough time. I'll take it up. Can you please? Yeah, here. I'm okay. I can mute people. Okay. Okay, yeah, let's take it up. I hope everyone got enough time to do it. And some decent discussion in the chat. Good. People asking about the square of an irrational number. Is that irrational? It's a really good question. Sometimes yes, sometimes no. Like pi squared is irrational. Pi is irrational and pi squared is irrational. But square root of 2 is irrational, and yet its square is just 2. And 2 is rational. So it's a good question, though. Good question. You're thinking about how irrational numbers work. Good. All right. So let's take it up. So solution for problem 1. Actually, you know what? I'll do it like this. I'll just move the problem lower so I have some more space. Okay. So let's take this one up. Okay. Is Q union this interval a field? I guess you could think of it. There's a lot of irrational numbers between -1 and 1. If I had to draw a picture of this, I'm going to try really bad to draw a picture. Here's the real number line. Here, let's say -1, or yeah, let's say -1 is here. And let's say +1 is here. So this set consists of all the numbers between -1 and 1, but it also includes all these rational numbers. So for example, it'll include 1.5, which might be over here. But it'll also include 1.25, which is over here, and the midpoint of that. So it kind of is, it includes all these rational numbers here, but not the irrational numbers. So it's kind of like, the way I think of it is like this, I know, which is kind of maybe weird, but there's kind of like, it's kind of spotty, but then I added in this interval. So in this interval, I get literally the entire continuum of real numbers. That's kind of how I think of it. And so I think, okay, can I come up with a real number can I come up with a way that this fails the axioms? And since it's the usual addition and multiplication, those operations are commutative and associative. So, those aren't the axioms that'll fail here. It's the answer is, by the way, it's not a field. So it's not a field. And the reason why, well, what I can show is that it's not closed under addition. I think you could show it's not closed under multiplication either. Here's a simple example. Did anybody, well, here, did anybody else get a, did anybody find an example of two real numbers, or sorry, two numbers in this field that whose sum is not in this field? Pi over 10 and 3. Good. Good. Pi over 10 and 3. Let's try that. If I do pi over 10, that's like 0.314159, right? That's pi over 10. And then he says 3. So if I do pi over 10 plus 3, that's going to be 3.314159, so on. And so you'd have to argue that this is irrational, that whatever this number is, it's irrational. And I guess you could make an argument based on, okay, look, it's irrational because if it was rational, then pi would be rational too. So you could say that. I guess that's pretty obvious. Another thing, let's see here. So this number is not in this set, according to this diagram, because this number is around here, right? It's 3. This number here would be pi over 10 plus 3. And as you can see, it's an irrational number. And the only irrational numbers in this set are here between -1 and 1. So I think this example works. Good. Thank you, James, for that example. An example of an irrational number. So this is in the set in question. And so is 3. Both are in my supposed field, but their sum is not. And therefore, it's not closed under addition. Good. Good. All right, let's take up the second one. This is a proof question instead. Here, I'll leave this there in case you want to start writing it down. So, well, scroll a little bit away. So let's solve this one now. For A, let's try. What do I have to prove? What do I have to prove to verify this first thing here? I have to verify that must check that -1 times x is the additive inverse. Of x. And how do I check that? I check that by adding it to x and seeing if I get 0. So i.e. that x plus whatever this element is, let's call it y. Let's call this whole thing y. I have to check that x plus y is 0. That's basically what I have to check. So let's try. X plus y equals x plus -1 times x. That's the definition of y. And I can write this first x as 1 times x. That's the definition of 1. And now by distributivity, I can factor out an x. I'm using distributivity backwards. So this is 1 plus -1 times x. So I should justify all these steps. Here, I'm using the fact that 1 times x equals x. Here, I'm using distributivity. Okay. How do I proceed next? 1 plus -1. Why is that 0? Well, by definition of -1, it's the inverse, the additive inverse of 1. So this is 0 by definition of additive inverse, since -1 is the additive inverse of 1. So you have to kind of check these things. I know it looks stupid. What's 1 minus 1? But you have to check these things. It's obvious for numbers, but for general fields, like the field of 4 elements, are you sure that 1 minus 1 is 1? You have to use the axioms to make sure you know. And then this last one, 0 times x. This is I think a theorem from the textbook. 0 times anything is 0. 0 times anything is 0. This is from the textbook. You have to prove this. And you can check the textbook or try to prove it as an exercise. Okay. Okay, so we're out of time. So what I want to do is take up B really fast. So suppose x plus y, what was that the question? X plus z equals y plus z. What I can do is add y, subtract z from both sides. And the way we subtract in fields is to add z, negative z. So I say x plus z plus negative z equals y plus z plus negative z. And let me do really gory detail here. Let me bracket it correctly. And now I say that by associativity, this is the same as x plus z plus minus z equals y plus z plus minus z. So this is associativity. Okay. Now I just use the definition of additive inverses. Z plus negative z, by definition of negative z, is 0. So this is x plus 0 equals, and then the same on the right side, y plus 0. And here I'm using the fact, literally the definition of negative z is that z plus negative z is 0. So you see, I'm being very careful about the steps I'm using. Imagine that you're in kindergarten and you didn't know about ordinary operations. You have to justify every step, just like in kindergarten. So x plus 0 is x, and y plus 0 is y. And that's by definition of 0. A plus 0 equals A for all A in F. Okay, so I proved it, I think. Yeah, I proved that x equals y. So I proved it. Good. So QED. Okay. Any questions about how these two proofs work? Yes. Okay. I guess I should have written a concluding. I'm going to stop recording shortly. I should have put a concluding statement here, I think. So I said x plus y is 0. Therefore, so since x plus y equals 0, it follows that y equals negative x. This is something called uniqueness of additive inverses. And this is a proposition from the textbook, that there's only one number y, or one element y, so that x plus y equals 0. And it's negative x. Okay. So that's how, you're right, I should put a concluding statement. Okay. So I think that's it for class. Thanks for coming, guys. I'll see you on Monday.